We'll see. I graded the question this time, and I was fairly happy with how you guys did the question I graded. So, equilibrium. The one thing I noticed was the directions said only rank A through E to make it easier, but I would say 90% ranks everything, not just A through E. Because when you rank A through E, it's a lot simpler, because the last one has this little wonky thing with the deprotonation event of the carboxylic acid, which drives the equilibrium to the right. Sodium hydroxide adds in, gives you OH, but under basic conditions the proton is quickly deprotonated. Yeah, I'd say about 50-50. A number of people wrote 50-50 lousy, equilibrium to be one. A number of people though did get the it's going to be deprotonated to drive it to equilibrium. But the key is up. Okay, so let's try to finish off chapter 19. And so this last half of chapter 19 is typically the stuff that people struggle on the most. So looking ahead, we're going to talk about aldol cyclizations. The answer for aldol cyclizations is things can go forwards and backwards. What eventually we're going to get for the major product is the most thermodynamically stable product. The most thermodynamically stable product. There's a little bit of a kinetic bend as well, and we'll talk about that in a second. Then we're going to talk about the Michael addition. So when you have a aldol dehydration product, which has a double bond in conjugation with the carbonyl, nucleophiles can add either into the carbonyl or into the conjugated olefin. And then we'll talk about the factors that influence whether or not we get carbonyl addition or olefin addition. And that's just kinetics versus thermodynamics. If the reaction can go backwards, it's going to favor 1,4. Because the 1,4 product is traditionally thermodynamically, so the addition into the olefin, not the carbonyl, is traditionally the thermodynamically favored product. Whereas addition into the carbonyl is traditionally the kinetic product. So if a nucleophile can leave, then it will favor 1,4. If a nucleophile can't leave after it forms the bond, it will favor 1,2. And we'll talk about more of that in a second. And then after that, we get into the Robinson annihilation, which is the reaction that it's of chapters 8-19. It's the legendary reaction. It's really not as hard as it looks. It's just an aldol dehydration followed by a Michael addition. But because it's two reactions back to back, what we call a domino reaction. Domino because it's something happens giving us a starting material for another reaction that happens. Even though it's two reactions we talk about a lot, generally the Robinson annihilation gives people a lot of problems. And so we'll talk about that. And then we'll talk about the Maddich reaction, which is like the aldol except with nitrogen. And we'll talk about that. So that will, I think we have a good 2 to 3 lectures of chapter 18 left. And then next week, we'll touch on chapter 19 real quickly, only the important things. And then the next week, we will have 2 lectures before final starts. So in lieu of giving a review session, the last 2 lectures, the week before final start, will be reviewed. So that's kind of what we're looking at. So aldol cyclizations. I'm just going to write in parentheses, thermo. Because as we talked about last week, aldols, because of the retroaldol, have the habit of being thermodynamically controlled. So if you can have multiple products form, then you will get the thermodynamically favored product as the major product. So here's an example that's in my notes. And so we have this ketone / aldehyde. But it has 3 alpha hydrogens that could all be deprotonated under general base conditions, and then form the resultant enolate that can add into the resultant carbonyl. And so because we have 3 different alpha hydrogens that can form the enolate, how many different products are we going to have? Possibly. Not that we actually have, but how many possible products are there? We have 3 alpha hydrogens, so we have 3 possible products. So the first product is from the base sodium methoxide and ethanol, for example, taking this proton, giving us a minus charge at this carbon, and then this carbon to the enolate will attack this carbon, giving us a 1, 2, 3, 4, 5, 6, 7, 8-membered ring. Yeah, I guess I can draw a stop sign, and so what I'm going to do is I'm going to do this carbonyl in green. And this carbonyl in black. And so since this carbon attacks this carbon, we'll have our aldol product. And I'm not going to draw the mechanistic intermediate, I'm just going to draw the aldol product after a proton transfer, so it will be protonated. And then, of course, we can do an aldol dehydration or not. Under these conditions, which I'll just say sodium methoxide and ethanol, we probably will not have the aldol dehydration happen, so we'll just get this. So there's one possible product, and that's if we take the hydrogen blue. Conversely, if you take the hydrogen in red, we'll form the minus charge here, and it can attack this carbonyl. And it'll give us a 1, 2, 3, 4, 5, a 6-membered. I'll do this one in green again, just show that this carbonyl is this carbonyl. And I'll do this in red and black as I did before. So again, this carbon attacking this carbon is forming this carbon, forming this bond. So I'll highlight in black the bond that's formed for each one. Then finally, the third possible product is the base taking this proton. And so if we take this proton in orange now, which is often the aldehyde, and attacks this ketone, it will give us a 1, 2, 3, 4, 5, 6-membered ring as well. And then now instead of having a secondary alcohol, we'll have a tertiary alcohol since it attacked a ketone. We form this bond. And just to keep the carbonyls in common, this was a green carbonyl. and this was the black. So my question for you are these three possible products. Which one is going to be the major product? Remember, everything is completely thermodynamically controlled. So saying it's completely thermodynamically controlled, are there any of these aldol products that we can X out and say, oh, it's much less stable, so it will just go back to a retroaldol and give us the starting materials? Which one? Blue, red, or orange? Blue? Well, everyone said it right. So, yes, the first one we can X out is blue because it's a 8-member drink. So which it can just easily do the retroaldol to give us our starting material back and go to something more stable. So because of that, we can go a nice big X over this one. Alright, so now we have these two 6-member drinks. So thermodynamically, they should be pretty similar because they're 6-member drinks. Which one of these products do you think will be favored though? So we get one major product, and we know it to be one of these two. Which one of these do you think will be favored and why? Orange or red? Why would orange be favored? Well, actually, if you say, to use the sterics argument, wouldn't red make more sense? Because in the red one, it's the enolate attacking an aldehyde, which is obviously easier than a enolate attacking a ketone. So actually, the favored product, because of the exact reason, is it's always going to be easier to attack a aldehyde than a ketone, is the red one is the major product. And so red versus orange isn't purely a thermodynamic thing. Red versus orange is just a kinetics thing, in that an aldehyde is always going to be more electrophilic than a ketone because of sterics, as well as a slight inductive effect with the methyl group on a ketone always putting in a little bit of electron density into the carbonyl, making it less reactive. Slightly less reactive. The big thing is sterics. So once again, think of stuff like that. Be perfectly honest, if I give you an example, I'll probably do it so the option is only 6-membered versus 8-membered. I wouldn't have this other kinetic thing. But I just want to point out the various factors that can lead towards one aldol favoring another. The big thing though is, if for a final perhaps, is 6 versus 8. Yeah?
Can you repeat again why the red one's favored over the orange one? I can't see it.
Yes. It's easier for an enolate to attack an aldehyde
Than a ketone?
than for an enolate to attack a ketone.
Okay. Thank you.
Yes.
They're all equally acidic, right?
Roughly within the same order of magnitude. But that's a very good question, right? We could definitely have in theory, one where there's one that's much more acidic, and then the more acidic hydrogen is just going to win. Yeah.
So the difference between aldol and glycine, which we were doing before, is that this takes off a beta.
The difference between the glycine and the aldol is with the glycine, when you attack an ester, we can have alcohol leave in the key tetrahedral intermediate. Whereas with a ketone and an aldehyde, there's no leaving group. So glycines, the ester has a leaving group in the OR group.
Okay.
Whereas the ketone, there is no good leaving group.
Okay, I got that.
So we get stuck at the alcohol.
Okay, but for the glycine, I think it said you can't take a hydrogen off of a tertiary carbon. Like, see it where it is?
Oh, yeah, yes. Okay, so you're saying...
Why can you do it on the aldol? With the red product?
Well, there's no... because...
It takes it off of the HB, right? It takes it off of the beta?
They both have it. Well, yeah, but remember, in order for the hydrogen to be acidic, it's got to be alpha to the carbonyl.
No, I know.
And they both have...
in the book, it said that you can't take it off of a tertiary, like...
But the book did all the way. I just stuck at the aldol product, whereas the book did the aldol dehydration.
Okay.
I think I'll go and do the aldol dehydration because it gives the arguments an even more oomph. So, So in this case, if we were to heat it up under the basic conditions, then we would get an aldol dehydration through, under basic conditions, a E2-like mechanism, right? So when we reflect this proton, electron density goes to the enolate. Enolate kicks, well, I guess I'll draw the intermediate. Where the space grabs the proton. Giving us the enolate intermediate. And then the enolate intermediate kicking off the alcohol as OH minus in the leaving group. To give us this as our product, so the aldol dehydration product. In this case, sorry, yes, I did do that. So it's actually this is body form. Sorry about that confusion. Still, so we formed the aldol product. I had an extra methylene in between when we really just wanted to be the enolate attached directly to what used to be the aldehyde carbon. So in this case, when we form the enolate, because of the sterics here, it's not going to work as well under basic conditions. It can still go, but it's going to be slower because of the steric bulk here. I don't know how much slower, but I believe that's what the book was saying, right?
Well, no, I was just confused because in the book it said you couldn't take a hydrogen off of a tertiary carbon.
Yeah, but we don't have any tertiary carbons.
So that's just an H.
with acidic
So that's just that's not a C then. That's just an H.
right here.
Yeah.
Yeah, that's an H.
Okay. No, on the where the red is, that's just an H. Yeah, I
right
didn't
here.
understand.
Yeah, that's his name. H.
Okay. Thanks.
Okay. But this dehydration can still do. It's just this hydration will go faster because of sterics. The key is they're thermodynamically controlled, so making really big, unstable rings won't happen. So if you have multiple options, look for the most stable 5 or 6 membered ring to form. If those intermediate gives you a 7 or 8 membered ring, it's just going to go back and funnel through a more stable ring system. And that's actually a concept we're going to talk about a lot when we're discussing the Robinson annihilation. So now that brings us to these ketones, these aldol dehydration products. And I'll just draw this one out. So alpha beta saturated ketones and aldehydes like this. So alpha beta unsaturated. So beta carbon, alpha beta, unsaturated. Unsaturated meaning they have less H's than they can optimally have. So unsaturated is a key word of saying double bond somewhere. So alpha beta unsaturated ketones and aldehydes have another kind of interesting reactivity. And this is not all that different than having a So from previous in the class, when we had a double bond in conjugation with a positive charge, what did that mean? It means we had resonance. So we could really draw this as a resonance hybrid, where the pi system was spread out equally throughout the 3-atom system, consequently meaning the positive charge was spread out through the double bond as well as carbon it was on. So instead of being a discrete carbon-cation, it was a 3-atom system where through resonance and conjugation, the positive charge was spread out throughout the entire system. So in reality, we had partial positive charge at both ends of the allyl-cation system. And so the nucleophile could add here or here, and it really just depended on what gave the more stable product, or more stable carbon-cation. So this was chapter 13 stuff, I believe? Or maybe chapter 12, but this was how thermodynamics versus kinetics of conjugated dienes. So do these alpha, beta, and saturated ketones remind you of a conjugated diene?
Yes.
Absolutely. Do you think they can do Diels-Alers? Yeah, they can. We're not going to do it in this class, but they're very similar to conjugated dienes. And so what that means is, we know that a carbonyl has a partial minus charge on the oxygen and a partial positive charge at the carbonyl carbon. So based on this, do you think this bond polarization is going to be seen or felt from this carbonyl?
Yes.
Absolutely, it's going to be. So I'm just going to draw a quick resonance structure. So here's the first carbonyl resonance structure. All right, so we've drawn this resonance structure several times. This is just explaining why the positive charge is at the carbon. And now we have our double bond that's in conjugation with the carbocation in this resonance structure. So we draw another resonance structure. Where the double bond can kick into the positive charge. And this gives us now something that's along the lines of this. So the carbon beta to the carbonyl by resonance is going to have a similar situation to the carbonyl carbon in that it has a partial positive charge. So we can think of this system almost like this resonance hybrid, where there are partial positive charges at both the beta carbon and the carbonyl carbon, and partial minus charges at the carbonyl oxygen and the alpha carbon. So let me draw this now as we'd actually draw it with the discrete bonds. But nothing changes. So in a alpha, beta, and saturated carbonyl, whether it be a ketone or an aldehyde or an ester or an amide or any electronegative group like a nitrile, has the same kind of deal. So this is the same kind of deal here with a nitrile or a nitro group or whatever. You're going to have a partial positive charge at your beta carbon and your carbonyl carbon, and a partial minus charge at your alpha carbon and your oxygen. With the nitrile, it'll be the same idea. Partial minus, partial positive, partial minus, partial positive. And all the electron withdrawing groups like nitro groups and sulfonyls have that same idea. Yeah.
So during the review section, you mentioned it's like typically easier to take away oxygen than it is to add it to a carbonyl for a base. So say you threw in like cyanide ion or some kind of.
All right. So cyanide, because of hybridization, is actually a surprisingly lousy base.
Okay, but which would it prefer, the carbonyl or the beta position?
We'll be getting into that.
Okay.
Take-home message as far as what goes into the beta or the carbonyl. If it's a reversible reaction, it's going to favor going into the beta position. If it's a reversible reaction, so something like methanol or an amine or an enolate, something with a pKa sub 25, it's going to favor going 1,4. If it's not a reversible reaction, so something like H minus or a Grignard adding in, it's going to favor 1,2. And I was just going to get there right now, so that's a good segue. So what this means is, when we take a nucleophile, the nucleophile can choose. It can either add straight 1,2, like we've talked about a lot in this class, like with sodium borohydride or lithium aluminum hydride, or Grignards or lithiums, organolithiums adding in. You can add 1,2. To give you a product like this. Or the nucleophile can add 1,4 at the beta carbon. So 1,2 in the carbonyl because it's across 2 atoms. 1,4 adding here because it's across 4 atoms. So it can add 1,4, and it'll give us a resulting enolate, which we would then have to quench with H3O to give us our 1,4 product. So again, nucleophiles can add 1,2 or 1,4. And as I alluded to real quickly, it's thermodynamically favored to go 1,4, but it's kinetically favored to go 1,2. So strong nucleophiles like Grignards, alkylithiums, sodium lithium aluminum hydride, sodium baryl hydride are going to go 1,2. Weaker nucleophiles like amines, cyanide, alcohols, enolates are going to go 1,4. And the reason being is when you have a strong nucleophile, give me a strong nucleophile.
ETO,
Which one?
ethyl oxide.
I didn't hear that.
Ethoxide.
Ethoxide, that's actually a weaker nucleophile.
Butyllithium.
Butyllithium, okay. So for instance, butyllithium, kinetically favored is going to be to go 1,2. The reason why 1,2 is kinetically favorable is because there's still more positive charge in that carbon than the beta carbon, because the carbonyl carbon is still closer to the oxygen than the beta carbon is. And so because it's closer to the oxygen, it doesn't only have a resonance effect, it also has an inductive effect. And remember, the inductive effect falls off quicker. And so whereas both the beta and the carbonyl carbon have the have the resonance effect, giving it a partial positive charge, because this carbon is closer to the oxygen, it's still got the inductive effect, which gives it a further positive charge, whereas this carbon is further away and has less of an inductive effect. So more positive charge of the carbonyl carbon. At the carbonyl carbon because of that inductive effect. And so it will then kinetically go 1, 2. And now you have this situation where can any of these groups be kicked out to go back to the starting material? Absolutely not. And the way to think about this is butyl lithium has a pKa of 50. The resulting alcohol has a pKa of 16. So basically, this equilibrium lies to the right by 10 to the 50 minus 16. So 10 to the 34. So more or less, this reaction can't go backwards. And so once something like Bewley, goes 1, 2, it can't go back. So it's stuck at the 1, 2 product until you quench the reaction. To get your tertiary product. So we've talked about chemistry like this before, yeah.
So if we have a nitrogen instead of an oxygen, would it attack the carbon?
It would be fairly similar. So instead of having an oxygen, you're having a nitrogen. It would be very similar.
But there would be less charge.
Yes, there would be less charge. So it would be a little bit softer. That's actually a really deep question. I don't want to open the Pandora's box, but as I was answering, I realized I remembered some literature precedents. It's complicated. The charge would be slightly different, and so the products would be slightly different, but I won't go there. Again, I love when people ask questions like that. It shows you guys are thinking about it in real time. So we favorited 1, 2. And just to give you some basic numbers, when you have a strong nucleophile, you normally get about 80 to 85% of the 1, 2 product. Oh, wrong thing. And you normally get about 10 to 20% of the 1,4 product. There's the bond forming for the 1,4 in this case. So it favors mostly the 1, 1, 2. So on a test, I would just ask for the 1, 2 product. The 1, 4 we get very little. And the reason we get any 1, 4 is because something like butyl lithium is so reactive. It's going to, it's stuck in the kinetic stuff, but of course when it's attacking, there's still a partial positive charge of beta carbon, so it can still attack to some degree. It's just going to prefer to attack the carbonyl more by basically a 4-to-1 ratio. Nonetheless, with a strong nucleophile, it's going to almost exclusively favor the 1, 2 addition product into the carbonyl. This double bond. So it adds in. Go ahead. So it adds in. It gives us an enolate like this, and then we quench it with H3O. So the intermediate from 1, 4 addition is going to be an enolate. And then when we quench it with H3O, the enolate can go to the carbonyl. So when you add 1,4, you get an enolate, which you then quench in your reaction. Okay? So now, I hear some murmuring. So strong nucleophiles like Grignards, lithium aluminum hydride, alkylithiums, really, really good nucleophiles whose conjugate acid has a pKa of pretty much greater than 40 will basically go 1,2. So then I can say pKa greater than 35 will go 1,2. However, things that can be good leaving groups are going to go 1,4. And so I'll go with the nitrile example, the cyanide example. Let's see if I have those correct numbers with me. So KCN, potassium cyanide, something I don't really like using in the lab.
Why not?
Cyanide? There's stories of there's actually people who have accidentally killed themselves by breathing in too much cyanide when they're doing chemistry. Because cyanide is actually a gas. And so if your potassium cyanide gets protonated, you have HCN. And if you breathe in HCN, let's say your hood's down, then not a very good outcome, right? So if you add in potassium cyanide, the product you'll get out almost exclusively is the 1,4 product. Via attacking 1,4, you form the enolate, then you protonate the enolate. I guess I do the cyanide in blue, so let me redraw it in blue. And so that's the product you get out. So why do we get 1,4 instead of 1,2? And so the answer is
Because it's a weak.
because it can be a leaving group. So it does probably add in 1,2 first. But cyanide is actually a fairly good leaving group. It has a pKa of about, I want to say 12. Don't quote me on that, but I think it's roughly has a pKa of 12. So that means it can go 1,2, but it can go backwards better to give us our starting materials again. So we can go forward and backwards, forward and backwards. Whereas, and it can always go forward and backwards regardless. This adds in, it can kick out nitrile, go to starting material, and add in again 1,2, and go forwards and backwards, forwards and backwards. Meanwhile, if it goes 1,2, sorry, if it goes 1,4, you get a product like this, and now it can only leave when the bond's rotated just right, so we have orbital overlap so we can kick off. But here's the thing, now we've got all these rotatable bonds in the product we formed. It is now very, very hard entropically to reach a conformation that can go backwards. And so because of this, because this is a much more flexible system, instead of being directly on the same carbon as the oxygen and gets electrons down, it's now 1, 2 carbons away. It's much tougher for it to be kicked off again because of the new flexibility of the system. And so then what happens is the equilibrium's got to look something along the lines of this, where it favors this guy, and then you throw in your H3O, and now you have something that's fairly stable. So because of this new flexibility you get in your system after you go 1,4, it becomes much harder for it to go backwards in order to actually obtain electron overlap. And because it's harder for it to go backwards, the equilibrium is going to favor 1,4, and that's how things go 1,4. So in general, if something is a good leaving group, something can leave in the 1,2 form, it will, and we'll favor 1,4. Here's another example. So Nick, you said sodium methoxide earlier.
Yeah.
So let's do an example with sodium methoxide. So let's make this a little easier case. Let's not have a pesky alpha hydrogen. So that way you don't have to worry about forming an enolate and other stuff. So let's just have a case that has no alpha hydrogen and it's just ready for a nucleophile to add. So we take sodium methoxide and add it in. It will probably go 1,2 first because 1,2 is indeed the kinetic product. Like so. But of course, you know, this can easily kick off one of the oxygens, no problem. And so, as easy as it was for sodium methoxide to add, it's just as easy for the sodium methoxide to be kicked off again to give us our starting materials. And so this 1,2 addition is always going to be an equilibrium going back and forth, back and forth. Meanwhile, the 1,4 addition the 1,4 addition is going to be much tougher to go backwards because the second we form this bond's got free rotation, and it can, remember for E1 and E2 eliminations, and what this step is, it's an E2 elimination. It's not that different than an aldyl dehydration step, right? The backwards reaction is very similar to an aldyl dehydration step. So we know it can happen. The issue is, it happens much harder than it does with this case. So it can go backwards, it's just much easier for this to go backwards in blue from the 1,2 addition to starting materials than it is for the 1,4 product to go backwards. And because the 1,4 product's not going to go backwards as much, eventually everything's going to funnel through something like this. And furthermore, if we're using sodium methoxide as the base, what's our solvent?
Methanol.
Methanol or ethanol, something, an alcohol. And so what that means is, and this is another thing that drives the equilibrium forward for this, in ethanol conditions, this enolate is going to be quickly protonated, right? enolate pKa 24, run ethanol pKa 16. Just gonna draw it here. This can be quickly protonated to give us our product under ethanolic conditions. Meanwhile, if this were to be protonated, and so I'm giving you a second reason as well besides the flexibility argument. If we protonate the 1,2 addition, can it still go backwards? Absolutely, right? It's still a lone pair of electrons next to the carbon. So even when this is protonated, it can go backwards to the starting materials. So under these ethanol conditions, if we protonate this, can this go backwards? This we know can go backwards, but it's not going to go as backwards as well as this. But under ethanolysis, we quickly protonate it to get this. Can this go backwards? Absolutely not. So which explanation do you guys like better, and I'll stick with it for next time? Do you guys like the flexibility argument? Or do you like the, even when this is protonated, it can still go back for 1,2, but when the 1,4 is protonated from the enolate, it cannot go back. Which one do you guys like better, and I'll stick to it?
Both.
The what? The second one? Alright, so both are fine, but I'll stick with the second one. So it's the idea that the protonated 1,2 addition can go backwards always, because it still has a lone pair of electrons adjacent to it. Whereas for a 1,4 addition, when it's protonated, it can't go backwards. But of course, I always try to keep an open idea here. Yeah?
How many equivalents of sodium oxide would you use for that?
Violent reaction?
Excess or just catalytic?
Excess, like 2 or 3 equivalents. So, on the day after tomorrow, or will we will talk about enolates adding it.